where we left off last week or the previous lesson was talking about how the periodic table structurally tells us also the structure of the atom. And we kind of looked at what we call the Bohr model, which I already had kind of introduced to you without you really knowing it, where we have this idea that in the what we call electron cloud, the surrounding area where electrons exist in the atom, because we know that the protons and the neutrons exist in the really dense mass center called the nucleus. But then we just know that, oh, for a neutral atom, the electron count must be the same as the proton count. But we don't really know where to put them. But when we look at the periodic table, partnered with the Bohr model, we learned something. And that is that there are specific rings or energy levels or rows where electrons can exist. And each of those rows has a specific number of seats available for those electrons. There's a max amount of electrons that can exist in each energy level, ring, or row, depending on what you're looking at. Okay. And so that's what we were looking at yesterday. And this was called the Bohr model. And we started unpacking how the Bohr model is shown in the periodic table. But there was one really key element to realize. The Bohr model is an old model. So the one flaw, major flaw it had was that it could not explain the transition metals. It could not include them. So we're definitely going to move on very quickly from the Bohr model. But what we do like about it is this idea of energy levels, distinct, exact rows, places where electrons can exist. It's not a free-for-all cloud like we thought originally, okay? So that's where we left off. And then I introduced this really important concept called valence electron concept. The electrons that are in the highest energy level for that atom. The electrons that are existing the furthest away from the nucleus. The electrons that have the least amount of Coulombic attraction between the nucleus and them. The electrons that are involved in bonding. The electrons that can be stolen away, right? The electrons that can be shared. Your appendage electrons, the electrons that interact with everything around them, okay? And I introduced this really important rule called the octet rule, that when we talk about bonding between valence electrons, we realize that we have a couple magic numbers. We have the number 8, okay, 8, and 8 is super important because it is the number that everyone wants to be valence electron-wise, not total electron count, but just valence. It's why we love the noble gases. Noble gases have 8. Have you guys heard of Henry VIII who like executed all of his wives? Yeah, pretty well-known number, right? So I don't know how you want to think about noble gases, but you could think about it of Henry VIII, royalty, right? Noble gases. He's quite the interesting, crazy person to study, okay? His wives weren't exactly sane either, but you know. But then we have this exception, because in chemistry and in life, there's always exceptions, right? We also have the second subpar rule that relates to our VIP elements, okay? I call them the VIP elements because they're in row 1, closest to the nucleus, and they only need 2. There's only a certain amount of spots for VIP. It's always less than the general public, right? So we have the duet rule, which is what we call for hydrogen and helium. They only want to and need to, which is why, by the way, helium is above the noble gases, even though in the column, the same column, even though it doesn't have 8, it acts like it's at completion. It acts like it's fulfilled. So we give it that role. We give it that status of being noble, of being complete. Okay. So out of curiosity, how many valence electrons on each of the following molecule? Lithium. 1. Oxygen. Calcium. Chlorine. And radon. 8. Because remember, Bohr model has totally ignores transition metals. The Bohr model does not account for that at all. Okay. And so that's why, even though radon is at a lower level, and if you count across, it looks like it should be like, you know, like 18. Thank you. It is not. It is, okay, 8. Because we only look at the main group elements, what we call them, no transition metals for the Bohr model. You guys got to remember, when I ask you certain questions, what stage of development are you thinking of? Are you thinking in the 1800s Bohr model stage, or are you going to be thinking in the future in the quantum mechanical model, which I'm going to introduce later this week? Okay. You got to take cues on what the prompt is asking you for what era of the model that you're focusing on. all right? Every model had some truth to it. We just kept on building it, making it more correct, all right? So good job, you guys, really good work. Out of curiosity, can I hear someone's summary for the structure? This is supposed to be in your own words. This is not for me, this is for you. Could someone offer a summary of the organization of the periodic table in their own words for me? Aislinn.
Columns indicate how many valence electrons there are, and rows indicate the energy level. So 1 through 7 is lower and more 2.
Excellent. So columns indicate the number of valence electrons. That's a great pattern to notice. Rows indicate the energy levels, right? And we have rows 1 through 7. Excellent. We also know that specific columns from the beginning of this unit, right? Elements in same column, okay, have similar properties. Okay. We also know from rows, right? Energy levels. But we also know, let's see, what else about rows? Honestly, there aren't really that much about rows other than energy levels that you know of so far. But don't forget, we count down. So N1 starts on top and then we go down to N7. That is something to remember. And the rows could be compared to as similar to rings or shells. Patterns, okay? Patterns. You kind of named them already in the description of columns, right? You can decide to rewrite. If you find any other patterns, you can let me know. But one thing that we do know is that everything increases by 1 proton number. We know that. That's a really common pattern about how the structure of the periodic table is, plus the other stuff. Okay. It is good to check in every once in a while with where you, with the big idea that you guys should be taking away, where you're at. I'm not going to always check in at the time that your brain needs it. If you start feeling overwhelmed, because you're going to start feeling overwhelmed soon about the stuff I'm going to introduce to you, because it's just totally thinking. Don't forget to be your own teacher in a sense of check in with yourself. Be your own kind of mentor. Be like, hey, you seemed overwhelmed right now. Maybe you just need to figure out what you know. Just figure out what you know. Take away my notes and just get blank piece of paper. What do I know about this topic? Draw yourself a little brainstorm diagram. Draw yourself a little table. Okay, I shouldn't and don't have to be and cannot be the only person that tells you these things, because I do not go home with you to remind you those things. So you need to be your own mentor and teacher and check-in point every once in a while too. But here's a great practice that I just wanted to give you guys. So we're going to look at proof, by the way. Today is going to be a lab where we're going to explore what's the confirmation. Proof is a bad word. What's the confirmation, the support that energy levels really do exist? Okay, we have this theory and it's like, well, how did we know that in lab? Because in the end, if you can't test it, you can't say it's true. You can create this giant theory, but if it doesn't show in the real world somehow in a measurable, quantifiable way, that's a problem as a scientist. So we're going to look at a lab that actually confirms to us this idea that energy levels do exist. And it's all about light emission. So here's what we need to understand, okay? There is a thing called quantum energy, and this goes off of the idea that there are distinct energy levels that electrons can exist. And electrons, if excited, can jump up an energy level, just like you and me. We can, right? The video, jump, right? So we say that quantum energy is a packet of energy. We call that a photon, by the way, that carries an exact, okay, and I don't know why I'm still in green. I don't know why that's necessary. An exact amount of energy, a distinct, exact amount of energy that resembles, right, this exact amount of energy jump or energy difference or energy distance, right? We know that there is energy that can be released in exact amounts. And we see this because according to the atomic structure, there are different energy levels at exact amounts, which means there's exact differences between them. Yes. Because you can have an exact amount of change. But that is triangle delta for change, Greek symbols. So we say that electrons in the neutral ground state, okay? They say they exist at the ground state, where we have the lowest energy arrangement. Lowest energy arrangement of electrons in a atom, or in an atom, to be annoying English. In an atom. So the way that we've been arranging our electrons so far is what we call the ground state. The way that you would think, you start by filling up the lowest ring, then the second highest, then the third highest. You don't just immediately put your first electron in row 3 and like, yeah, that's where it goes. No, we naturally assume that we build what we call from the bottom up. We start with the lowest energy level and we fill that with the electrons that we have. And then if we have more, we move on to the next, right? So from an illustrative point of view, okay, we know that we fill electrons starting here and then up to here. We do not fill, okay, so I'm going to put a check mark for the ground state, right? This is ground state, lowest energy arrangement. We start with n equals 1, energy level 1. We go into n equals 2, energy level 2. We do not, on the other hand, okay, start by filling, and I don't know how you want to draw this, but I would say I wouldn't start by filling the 3 here, right? And leaving row 1 empty. Like that doesn't make any sense. That's a big no-no, okay? We don't do that. If I have 3 electrons, I start with row 1, energy level 1, ring 1, and then I go out, right? And you're like, that seems obvious. That's a big thing to confirm in science, because that messes you up if you don't have that assumption, okay? So, but then we have this thing called excited state, because we know that we can shoot energy at electrons and atoms in general. Like, you know that you can warm something up. That, like anything, is full of atoms. If you warm it up, you know something's happening. It boils, it bubbles, it melts, whatever. You're literally inserting energy into those atoms, and those atoms are absorbing that energy. All right. So we already kind of know this to be true from a macroscopic level. Like if we're made of atoms and we see macroscopic properties absorb heat, then those atoms making up those macroscopic properties are also absorbing the heat. And we say that when electrons, okay, absorb energy, they jump up to another level. They have the energy to jump. So the excited state is a higher energy, okay, arrangement of electrons, where electrons jump up levels. It doesn't have to be 1 level. It could be 2. It could be 3. It could be a whole series. I don't even know. But it jumps up levels with energy absorption. With energy absorption. Okay? It jumps up a level with energy absorption. Now, what would this look like with the Bohr model? What would this look like with the Bohr model? Let me move this here. Okay, what it looks like is, let's say I have high energy. Energy enters my atom. Okay, I shoot it with a laser. What's going to happen is maybe this electron jumps up here and goes to this ring. Okay, it could do that. That electron could jump up and go up to this ring. Okay. But what happens is, what we see is though this excited state doesn't last forever. Because there's a little principle in the world known as low energy is better, right? You guys know this because I have seen you do back bending stunts to pick up a pencil that's 2 feet away from you. Oh my God, I just hit, that was gross. That's 2 feet away from you. Instead of just getting up and moving. Like, I don't know how that saves you much energy, but we all try to exist at a super low energy. All right. And the same is true here. So the ground state is always what we call the preferable state. Like we want to stay at the ground state if possible. But the excited state is a temporary state. It happens in the right conditions. It's a temporary state. And so when we look at excitation of electrons or excitation of atoms, we see that stage one, you start at the ground state, right? Everybody starts at a ground state, low energy. Okay, stage two, okay, you get energy absorption. You absorb energy absorbed. So your electrons jump, okay, to a higher level. And then stage three is that your electrons don't want to stay up there. That's actually not very stable. Being high energy isn't stable at all, right? Like try jumping in midair and staying up there. It's not going to happen. One, because of gravity, but notice gravity is like analogous to this fundamental concept in the world that we want to be low energy, right? So what happens is that energy is then released. And the electron falls back down to ground state. It falls back down, kind of like, right? You start on the ground. You jump, you come back down. Okay, but there's something really cool that happens with this, that because you're still not seeing probably like, where do I see this in the lab then? How do I know that this is true in the lab? Well, remember, if we have energy at distinct energy amounts, and we know energy is a wave, and we know waves can have color, then we often see that energy being absorbed and then released as a color. And it's not a spectrum of color. It's not like every single color is in one. We see a distinct color. And that tells us that there was a distinct amount of energy jumped up and then jumped back down. And that is where we see the confirmation of energy levels. Through this idea that, well, if I shoot energy, a distinct quantum amount of energy in a particle known as a photon is a particle of light. It's literally a particle of energy. It's a wave particle. It's a particle that's a wave. And it is absorbed by an atom. My ground state low energy atom is going to get excited. It's going to have its electrons jump. And it jumps randomly. It jumps a series. Like, I don't know if it jumps from just level 1 to level 7. Maybe it jumps from level 1 to 3. Doesn't matter. It jumps, and there's a distinct amount of energy difference that's associated with that jump. And when that jump occurs, it has to fall back down and release that energy again, right? So once that jump occurs, afterwards, though, it's got to fall back down and release that energy again. And that energy is light that's released in a distinct amount of color based off of that distinct jump height. And that light or color is used to tell me, one, the identity of that atom, because each atom has unique electron jumping patterns, but two, confirm the idea that indeed we do have energy levels. Pretty sick, eh? Yeah. Someone figured this out. Like, I didn't figure this out. It's pretty cool. So we can identify elements based on the light they emit, okay? We can figure this out because here's why. Every element has a unique electron jump pattern. So if I'm helium, I have 2 electrons that can jump. I have 2 electrons available to me. If I'm, silicon, I have 14 electrons that can jump. I have 14 unique lights that together make a spectrum, a pattern of light that is unique to that element. My 14 electrons can create 14 unique jumps that together create like a puzzle or an ID or an identification, a color identification for that element. And they're really, really cool. The spectrums, we call them spectras or spectrums, the light spectras are super cool. And they're not just a huge continuous spectrum, they're distinct energy light amounts that represent each jump that the electron in that atom went through. And that unique light pattern is the ID of that element. Yes.
So each element has a spectrum in itself of the light of the electron.
Yep. Yep. So let me just kind of skip down to the next page and let me give you a little quick overview. Okay. So here's our electromagnetic spectrum. And I really should have probably looked this up because I actually don't have this memorized myself fully. But here's the idea. So pardon me on my phone. I'm just looking up the electromagnetic spectrum. Oh, magnetic spectrum. I had to memorize this a long time ago. And what do they say? If you don't use it, you lose it. Here is me losing it. Okay, so we have on the electromagnetic spectrum, which by the way is it's the, how do I describe this? It's like the, well, I don't want to use the word spectrum. Yeah, sure, whatever. It's the spectrum. That's a bad definition if I had to use the word in it. Okay. It's the spectrum of all possible waves. Okay, or energies in the world. So what we have for the electromagnetic spectrum is we have at the low energy, okay, this is the low energy side, and this is the high energy side. At the low energy side, we have radio, okay, radio waves. Then we have microwaves. Then we have what we call IR infrared waves, infrared. And then we have this unique little portion called visible, which is what we care about. This is what we function off. And then as we go higher energy, we have UV, what we hate about the sun, right? UV protectant. We have X-rays for all you that break your bones. And then we have gamma rays. Gamma rays are what kill you. It's radiation. Okay. If you have low energy, you have long wavelengths. If you have high energy, you have short wavelengths. Right? And that's what the image above is what's a wavelength? It's the distance between each peak in a wave. So high energy wavelengths have short distance between them and high frequency because you can fit a lot in a small amount of time. Okay. Low energy, long wavelengths. For us in particular, this is what we see. We look at the visible light spectrum when we talk about, when we talk about conformation, electron jumping. We look at this unique spectrum with invisible light. Yes.
Is visible light exactly in the middle?
No. It's how my handwriting worked out. And we know that the color goes from this. Within the visible light, you have what we call Roy G. Biv. Roy G. Biv. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet are the visible colors on the spectrum within the visible light range. Red is actually low energy compared to blue, which is the exact opposite of how we use it in models. Red is actually a low energy color. Yep, it does go in this order. Red, then orange, then yellow, then green, then blue. That is a G. Blue, then indigo, then violet. This is increasing energy. It goes this direction. Okay. So we can excite atoms and figure out a unique color spectrum that's released from them to not only confirm the idea of energy levels, but also use to identify them. Quick note from above, just in case you haven't taken physics, the wavelength is the distance between the peaks right? And the frequency is how many peaks occur in a certain amount of time in a given time interval. Like how often, right? It seems pretty self-explanatory. Honestly, if you already know this stuff, I wouldn't even waste your time writing it down. Okay, but for those of you that, for those of you that don't know this stuff, like, there you go. And by the way, there's a really important principle that goes along with this. Okay, because I've been talking about already this idea that light is a wave, but light can be absorbed as a particle. This discovery also revealed a very unique principle known as de Broglie, because he was a scientist, who suggested a dual nature, that matter and energy are actually essentially the same. Essentially, right? We call this wave particle duality. Okay, that waves have particle characteristics and that particles have wave characteristics. Okay, so for example, photons are particles of wave energy. Photons are particles of wave energy. And wave energy is a particle. Yes.
Would it be possible to have a wave in a like a area without any particles?
The idea, oh, so this goes into a different theory, that question that you don't have to know about. It's just a cool theory if you go into higher level chemistry. It's called Schrodinger's theory. His analogy was if you had a cat, it's called Schrodinger's cat, and it was in a box and it was alive and dead at the same time. But the moment you open the box, the cat's dead. Same idea with analyzing all this stuff, the particle and the wave nature. They technically coexist until you try to quantify one of them, then you can only see the one version. So if you try to quantify the particle nature of a wave, you will only be able to see the particle nature. If you try to quantify the wave nature, you cannot see the particle nature. It's kind of like how when we look at people's eyes, we actually look at one eye. We don't look at both.
Is there a theory you like with Schrodinger's theory?
I just think it's cool. I always thought Schrodinger's cat was super cool. Like how trippy would that be to be alive and dead at the same time, right? I think it's also really cool because it acknowledges the limitations of science. Science is limited. Science is amazing. The fact that we could even figure that out. It is also limited because even science says, yeah, as a theorem, as like a principle of science, we cannot do this at the same time. We have to focus on one. It also means that there's a need for high collaboration, right? One group focuses on this, another group focuses on that. It's just cool. It's just super, super cool. But the cat really gets me. I really like the cat analogy. Yeah. Okay. So that's a lot. That's a lot of weirdness. The world is weird, but it's weird in a beautiful way. Kind of like arguably you. Maybe you are just weird. Okay. But let's assume that you're weird in a beautiful way, right? So, because it is Valentine's, let us be gracious with our thoughts. And so what we're going to do is we're going to really just take a moment to kind of have fun and appreciate this. And it's really more of a fun lab. Like it's supposed to be fun. So for those of you at home, sorry that you missed today. That's a bummer. And otherwise, don't forget that we have a quiz, test on Wednesday and quiz on Thursday for spring 2023, or at least whoever's watching this in the future, it'll be coming up real close. And let's go ahead and transition to lab. So please pull out your lab handout and get lab ready for me, and I'll walk you through the instructions.